any kind of questions? There were a few questions about the homework. Casey, you have that problem with e to the minus t? E to the minus t? Let's do that in class because there were several people who faced that problem. You faced it and you got it, and can I cheat? Can I take your work so I can present it at the board? I'm serious about it. So I know we've done this together. I don't even remember the problem. How was it? Homework problem. The one with the e to the minus 2. Can you tell me, Casey, can I drop the statement?
Well, Wi-Fi is being slow, so...
If you find it, give it to me. I'll give you $2. Oh, is this one? No? Oh, no, not this one. Can I have it from you? I won't give you anything. So can somebody give me that? That's it. That's my handwriting.
Yeah, I know.
Okay, all right. So the problem says, it's a good reading problem, I have no idea. It's the one that has x of t equals e to the minus b cosine t, y of t, and you go, by your exclamation, I understand that you love this problem. And so you've had this type of path integral, compute the path integral with respect to the arc length element. Well, Magdalena, write slowly because nobody's rushing you. Integral over C of the integrand will be a very nice friend of yours, x squared plus y squared. But of course, they are both functions of t in general, and you have the ds element. And what does this mean? S is little s. It means that your arc length element should be expressed in terms of what? Who in the world is the arc length infinitesimal element? It's the speed times dt. Say it again. It's the speed, and what was the speed? R prime of t dt. Right? So you will have to transform this path integral into an integral with respect to t, where t takes values from a t0 to a t1. And I don't want to give you your notebook back. Okay, no, I'll do the same thing all over again, and you control me, and then if I do something wrong, you tell me. And what was the path? Specified as what? Yeah, the path was
0 to pi by 2.
t equals from 0 to pi over 2. I have to write it down. So let us write the r prime of t, the speed, square root of x prime of t squared plus y prime of t squared, because this is a planar curve. Before we do that, we have to go ahead and compute x prime and y prime. And of course that's product rule, and I need a better marker. Yes, sir.
The arc t, if we take as the arc,
This is the...
I would consider it as a path function that looks like arc, or I'm thinking that it's missing one, or doesn't missing one. Plus one.
No. Okay, let me explain. So suppose you are along this arc, right? In plane. And this is your r of t.
Okay.
And that's called the position vector, and that's x of t, y of t. Okay, what is your velocity vector? Velocity vector will be a tangent to the curve. Suppose you go in this direction, counterclockwise, and then r prime of t will be this guy.
Yeah.
And he's going to be x prime, y prime. And we have to find its magnitude. And its magnitude will be this animal. So the only thing here is tricky because you will have to do this carefully, and there will be a simplification coming from the plus and minus of the binomial. So a few people missed it because of that reason. So let's see what we have. Minus e to the minus t, first prime, times second unprime, plus the first unprime times the second prime. Good. We are done with this first guy. The second guy will be minus e to the minus t sine t. Why do I do this? Because I'm afraid of this being on the final. Well, it's good practice. You may expect something a little bit similar to that. So why don't we do this as part of our review? Which would be a very good idea. We are gonna do lots of review this week and next week already, because the final's coming close and you have to go over everything that you've covered. Let's square them and add them together. Okay. When we add them together, this guy, the speed, Mr. Speed, is going to bless you. Is not going to bless, it's going, okay, you are being blessed, and now let's look at that. You have e to the minus 2t cosine squared, and e to the minus 2t sine squared, and when you add those parts, the sine squared plus cosine squared stick together, they form a block called 1. Do you guys agree with me? So what we have as the first result of that will be this guy. But then, when you take twice the product of these guys in the binomial formula, and twice the product of these guys, what do you notice? We have exactly the same individuals inside, but when you do twice the product of these two red ones, you have minus, minus, plus. But when you do twice the product of these guys, you have minus, plus, minus. So they will cancel out. The part in the middle will cancel out. And finally, when I square this part and that part, what's going to happen to them? And I'm going to shut up because I want you to give me the answer. Square this animal, add them together. What do you have?
Square,
e to the minus 2t, so exactly the same as this guy. So all in all, under the square root, I'm going to get square root of 2 times e to the minus 2t, which is e to the minus t square root of 2. Am I right, Nitish? That's what we got last time as well. So I know who this will be. I don't know who this will be, but I'm going to need your help. Here I write it, x squared of t plus y squared of t. In terms of t, squaring them and adding them together, it's going to be again a piece of cake because we've done it. How much is it? I'm waiting for you to tell me. This is this one.
Yeah. Square is square.
E to the?
Minus 2.
And anything else?
Was it 2? Cosine squared t. Times
No.
2.
2 times 2.
Y times a 2.
Yeah, times 2 in the last one. Because we had an e to the minus 2t plus an e to the minus 2t.
So I took this guy and squared it. And I took this guy and squared it.
No, we don't have it.
And I sum them up. And I close the issue. And yes, I have sine squared plus cosine squared, which is 1.
Yeah.
So it's just e to the minus 2t. Agree with me?
Yeah.
All right, now we have all the ingredients. Do you have all the ingredients we need? We have this, we have that, we have that. And we should just go ahead and solve the problem. So, integral from 0 to pi over 2. This friend of yours, e to the minus 2t, was the integrand. The speed was over there. e to the minus t times square root of 2. That was the speed on prime in magnitude dt. Is this what we got? All right. Now, we are almost done in the sense that we should wrap things up. Square root 2 gets out, and then integral of e to the minus 3t from 0 to pi over 2 is our friend. We know how to deal with it. You have dt. So, when you integrate that, what do you have? Let me erase.
Negative square root 2 over 3 e to the minus 3t.
Right, so let me erase this part. So we have, first we have to copy this guy. Then we have e to the minus 3t divided by minus 3, because that is the antiderivative. And we take that between t equals 0 and t equals pi over 2. Square root of 2 says I'm going out. And actually minus 3 says also I'm going out. So he doesn't want to be involved in this discussion. They are both going out. Now, e to the minus 3 pi over 2 is the first thing we got, and then minus e to the 0. What's e to the 0? 1. So in the end, you have to change the sign. You have root 2 over 3 times bracket. Notation when you type this in web work, because based on your syntax, if your syntax is bad, for example, here you will have to put caret minus 3 pi over 2. Are you guys with me? Do you understand the words coming out of my mouth? So here you have to type the right syntax, and you did, and you got.
And I didn't got the answer. I need to type the decimal answer in terms of decimal place.
This is a problem. It shouldn't be like that. Sometimes, unfortunately, well, fortunately, it rarely happens that a web work program does not take your answer in a certain format. Maybe the pi screws everything up, I don't know. But if you do this with your calculator eventually, and what was the approximate answer you got, Nitish?
0.467.
And blah, blah, blah. I don't know. I think web work only cares for the first two decimals to be correct. As I remember. I don't know, but as I remember, I have to ask the programmers. So this would be approximate. You plug in the approximate answer. I solved the problem, so I should give myself the credit, plus a piece of candy, but I hope I was able to save you from some grief, because you have so much review going on that you shouldn't spend time on problems that give you a headache for computational reasons. Actually, I hate computational reasons because we are not androids and we are not computers. What we can do is think of a problem and let the software solve the problem for us. So our strength does not consist in how fast we can compute, but on how well we can solve a problem so that the calculator or computer can carry on. All right. I know I covered up to 13.6, and let me remind you what we covered. We covered some beautiful sections that were called 13.4. This was Green's theorem, and now I'm really proud of you that all of you know Green's theorem very well. And the surface integral, which was 13.5. And then I promised you that today we would move on to 13.6, which is Stokes' theorem, and I'm going to do that. But before I do that, I want to attract your attention to a fact that this is a bigger result that incorporates 13.4. So Stokes' theorem is a more general result. let me make a diagram, like a Venn diagram. This is all the cases of Stokes theorem, and Green's is one of them. And this is something you've learned, and you did very well, and we only consider this theorem on a domain that's simply connected. It has no holes in it. Green's theorem can be also taught on something like a donut, but that's not the purpose of this course. You have it in the book, it's quite sophisticated. 13.6 starts at, oh my God, I don't know the pages. And being a co-author of this book means that I should remember the pages. All right, there it is. 13.6 is at page 1075. Okay, and let's see what this theorem is about. I'm gonna state it as first Stokes theorem, and then I will see why Green's theorem is a particular case. We don't know yet why that is. Well, assume you have a force field. May the force be with you. This is a big vector value. Function over a domain in R3 that includes a surface S. We don't say much about the surface S because we try to avoid the terminology, but you guys should assume that this is simply connected surface patch with a boundary C. Such that C is a Jordan curve. We use the word Jordan curve as a boundary of the surface, but we don't say simply connected, and I'm going to ask you, what in the world do we mean when we say simply connected? I've used this before. I just want to test your memory and attention. Do you remember what that meant? I have some sort of little hill, or S could be a flat disc, or it could be a patch of the plane, or it could be just any kind of surface that is bounded by a Jordan curve C. What is a Jordan curve? What can we say about C? So C will be nice, piecewise continuous. We assume the continuous actually in most cases. No self-intersections. So we knew that from before, but what does it mean is simply connected for us? I said it before, I don't know how attentive you were. Connectedness makes you think of something. No holes in it. So that means no holes, no punctures. No holes, no punctures. So what I don't draw it, I will draw it so you can laugh. Assume that the dog came here and took a bite of this surface. And now you have a hole in it. Well, you're not supposed to have a hole in it, so tell the dog to go away. So you're not going to have any problems, any puncture, any hole, any problem with that surface. Now the surface is assumed to be a regular surface. And we've seen that before. And since it's a regular surface, that means it's immersed in the ambient space, and you have an N, orientation. Orientation, which is the unit normal to the surface. Can you draw it, Magdalena? Yes, in a minute I will draw it. At every point you have an N, unit normal. What was the unit normal for you when you parameterized the surface? That was the stick that had length 1, perpendicular to the tangent plane, right? So if you wanted to do it for general R, you would take those R sub U, R sub V, the partial velocities, and draw the cross product. And this is what I'm trying to do now. and just make the length be 1. So if the surface is regular, I can parameterize it as an immersed surface, then n will exist as an orientation. I want something more. I want n orientation to be compatible to the direction of travel. On C, along C, along, not on, but on is not bad either. So assume that this is a hill and I'm running around the boundary. Look, I'm just running around the boundary, which is C. Am I running in a particular direction that tells you I'm a mathematician? It tells you that I'm a weirdo. Yes. So in what kind of direction am I running? Counterclockwise. What? Because I'm a nerd, like Sheldon or something. So let's go around. And so what does it mean I am compatible with the orientation? Think of the right-hand rule, or forget about right-hand rule. I hate that word. Let's think faucet. So if your motion is along the C, so that it's like you are unscrewing the faucet, it's going up. That should mean that your orientation n should go up, or not down, in the other direction. So if I take C to be my orientation along the curve, then the orientation of the surface should go up. Am I allowed to go around the other direction on the C? Yes, I am. That's, how is this called? Inverse trigonometric, or how do we call such a thing?
Clockwise.
Clockwise, you guys are genius. Okay, clockwise. If I would go clockwise in plane, then the n should be pointing down. So it should be oriented just the opposite way on the surface S. All right, that's sort of easy to understand now, because most of you are engineers and you deal with this kind of stuff every day. What is Stokes' theorem? Stokes' theorem says, well, in that case, the path integral over C of f dr, f dot dr, what the heck is this? I'm not going to finish the sentence because I mean, there is a sentence there, an equation, but I mean. So I'm asking you first, what in the world is this? F is the, may the force be with you. R is the vector position. What is this animal? The book doesn't tell you. This is the work that you know so well. All right. So you may hear math majors saying they don't care. They don't care because they are not engineers or physicists, but work is very important. The work along the curve will be equal to, now comes the beautiful part. This is the double integral over the surface like this with respect to the area element ds. Oh, guess what? You wouldn't know unless somebody taught you before coming to class. This is going to be curl F. What is curl? Is a vector. So I have to do dot product with another vector, and that vector is n. And some people read the book ahead of time, which is great. I would say 0.5% or less of the students read ahead in a textbook. I used to do that when I was young. I didn't always have the time to do it, but whenever I had the possibility, I did it. Now, a quiz for you. No, don't take any sheets out, but a quiz for you. Could you prove to me, just based on this thing that looks weird, that the Green's theorem is a particular case of this? So prove, where should I put it? That was Stokes' theorem. Stokes' theorem. And I'll say exercise number 1. Sometimes I put this in the final exam, so I consider this to be important. Prove that Green's theorem is nothing but a particular case of Stokes. Then I make a face in the sense that I'm trying to build trust. Maybe you don't trust me, but let's do this together. Let's prove together that this is what it is. Now, the thing is, if I were to give you a test right now on Green's theorem, how many of you would know what Green's theorem said? So I'll put it here. Open an icon. Imagine this would be a icon or a window on the computer screen. Like a tutorial reminding you what Green's theorem was. So Green's theorem said what? We have to bless you. So Xander started the theorem by, we have a domain D that was also simply connected. What does it mean? No punctures, no holes, no holes. Even if you have a puncture that's a point, that's still a hole. You may not see it, but if anybody punctured the portion of the plane, you are in trouble. So there are no such things. And C is a Jordan curve. And then you say, okay, how was it? How was F? F was a C1. What does it mean that F is a C1? F is a vector valued function that's differentiable, and its derivatives are continuous, partial derivatives. And so you think F of xy will be m of xy I plus n of xyj. It's a vector field, so it's a multi-variable, so it has two variables, okay? So you think, okay, I know what this is like. If this would be a force, if this were a force, I would get the vector, the work. How can I write this again? We didn't write it like that. We wrote it as m dx plus m dy, which is the same thing as before. Why? Because Mr. F is mi plus nj, not k Magdalena. You were too nice, but you didn't want to shout at me. And dr was what? Dr was dxi plus dyj, right? So when you do this dot product, which is called work, the integrand will read m dx plus n dy, and this is what it was in the Green's theorem. And what did we claim it was? Now you know it because you've done a lot of homework. You're probably sick and tired of Green's theorem, and you say, I understand that work, a path integral can be expressed as a double integral some way. Do you know this by heart? You proved this to me last time. You know it by heart. That was n sub x minus m sub y, and we memorized it. dA over, this is a planar domain. It's a domain in plane D in plane. You have two. I said it, but I didn't write it down. So double integral over d n sub x minus m sub y dA. We've done that. That was section, what section was that, guys? 13.4. Yeah, for sure you will have a problem on the final like that. Do not expect lots of problems. Do not expect 25 problems. You would not have the time. So you'll have some 15, 16 problems. This will be one of them. You mastered this Green's theorem. When you sent me questions from web work, I realized that you were able to solve the problems where these were very easy to manipulate, like constants and so on. That's a beautiful case. There was one that gave Nitisha a headache, and then I decided, number 22, right? Where this was more complicated as an integrand in y, and guys, your domain was like that. And then normally to integrate with respect to y and then x, you would have had to split this integral into two integrals, one over part of the triangle and the other one over part of the triangle. So the easier way was to do it how? To do it like that, with horizontal integrals. And we've done that. I told you, I gave you too much. Actually, I served it to you on a plate, the proof, the solution of that problem, but you have many others. Now, how do we prove that this individual equation that looks so sophisticated is nothing but that for the case when S is a planar patch? If S is like a hill, yeah, then we believe it. But what if S is the domain D in plane? Well, then this S is exactly this, D. So it reduces to D. So you say, wait a minute, doesn't it have to be curvilinear? Nope. Any surface that is bounded by C verifies Stokes' theorem. Say it again, Magdalena. Any surface S that is regular, so on, within the conditions of the theorem, that is bounded by Jordan curve will satisfy the theorem. So let's see what that becomes. That should become a friend of yours, and we already know who this guy is. So the integral of the R is your friend, integral m dx plus n dy. That's staring at you over C. It's an integral over one form, and it says that's work. On the right-hand side, it's a little bit more complicated. So we have to think. We have to think. It's not about computations, about how good we are at identifying everybody. If I go for this particular case, S is D, right? Right. So I have a double integral over D. Sometimes you ask me, but I saw that over a domain that's a two-dimensional domain, people wrote only one snake. It looks fat, like somebody fed the snake too much. Mathematicians are lazy people. They don't want to write always double snake, triple snake. So sometimes they say, I have an integral over an n-dimensional domain. I'll make it a fat snake. And that should be enough. Curl F in. We have to do this together. Is it hard? I don't know. You have to help me. So, what in the world was that? I pretend I forgot everything. I have the amnesia.
Del over del x.
Yeah. So actually, some of you told me by email that you prefer that. I really like it that you. Maybe I should have started a Facebook group or something, because instead of the personal email interaction between me and you, everybody could see this. So some of you tell me, I like better this notation because I use it in my engineering course. Curl F. Okay, good. It's up to you what you want to use. D dx, D dy. I'm in principle in R3, but I'm really lucky because in this case F is in R2 value. In R2.
DDZ?
Huh?
DDX, DDY, DD.
I'm sorry, you're so on the ball. Thank you, Sam.
No, I thought I completely misunderstood what Pearl was momentarily.
No, I wrote it twice. So m and n and 0. M is a function of x and y only. And of course, do I have to write that? No, I'm just being silly. And what do I get in this case?
Negative and no, you don't. There's
N is minus alpha.
I times this guy. How much is this guy? 0. Why is that 0? Because this contains no z, and I prime respect to z, so that is nonsense. 0i minus 0j. Why is that? Because 0 minus something that doesn't depend on z. So plus, finally, the only guy that matters here is this determinant, which is this, which is that. So because I have derivative of n with respect to x minus derivative of m with respect to y, and now I stare at it and say times k. That's the only guy that's not 0, the only component. Now I'm going to go ahead and multiply this in the dot product with n. But we have to be smart and think n is what? is normal to the surface, but what if the surface is a patch of the plane? The normal would be trivial. What will the normal be? The vector field of all the pencils that are K.
Yeah.
K, it's all K. K everywhere, all over the domain is K, so N becomes K. Where is it? There. N becomes K. So when you multiply in the dot product this guy with this guy, what do you have? N sub x minus M sub y dA. QED. What does it mean, QED? $1, which I don't have, for the person who would tell me what that is. In Latin,
Acquiring.
quod erat demonstrandum, which was to be proved. Yes? So I'm done. When people put QED, that means they are done with the proof. But now, since mathematicians are a little bit illiterate, they don't know much about philosophy or linguistics, now many of them, instead of QED, they put a little square box. And we do the same in our book, so that means I'm done with the proof, let's go home. But not now, okay? So we proved that for the particular case of the planar domains, Stokes theorem becomes Green's theorem, and actually this is the curl, and this, well, not the curl, but you have the curl multiplied, curl of f multiplied with dot product with k, and this green fellow is exactly the same as n sub x minus m sub y, smooth function, real value function. Okay. All right, am I done? Yes, with this exercise 1, which is a proof, I'm done. You haven't seen many proofs in calculus. You've seen some from me that we never cover. We don't do epsilon delta in regular classes of calculus, only in honors and not in all the honors. You've seen some proofs with epsilon delta. You've seen 1 or 2 proofs from me occasionally, and this was one simple proof that I wanted to work with you. Now, do you know if you're ever going to see proofs in math classes? Out of curiosity. Depends how much math you want to take. If you're a math major, you take a course called 3310, that's called Introduction to Proof. If you are not a math major, but assume you are in this dual program, we have a beautiful and tough dual major, mathematics and computer science, 162 hours. Then you see everything you would normally see for an engineering major, but in addition you see a few more courses that are based on proofs. And one of them is linear algebra. Linear algebra 2360, we do a few proofs. Depends who teaches that. And in 3310 also, you see some proof like by way of contradiction, let's prove this and that. Okay, so it's sort of fun, but we don't attempt long and nasty, complicated proofs until you are in graduate school normally. Some of you will do graduate studies, most of you will, some of you, I know 4 of you want to go to medical school. And then many of you hopefully will get a graduate program in mathematics, in engineering. Okay, let's see another example for this section. I don't particularly like all the examples we have in the book, but I have my favorite. And I'm gonna go ahead and choose one. There is one that's a little bit complicated, and you asked me about it, and I wanted to talk about this one because it gave several of you a headache. There is example 1, which says, what does it say? Evaluate path integral over C of 1 over 2y squared dx plus z dy plus x dz, where C is the intersection curve between the plane x plus z equals 1 and the ellipsoid x squared plus 2y squared plus z squared equals 1. That's oriented counterclockwise. As viewed from the above picture, and I need to draw the picture. The picture looks really ugly. You have this ellipsoid. And when you draw this intersection between this plane and the ellipsoid, it looks horrible. And the hint of this problem, well, if you were to be given such a thing on an exam, hint would be that projection, look at the picture, the projection of the curve of intersection on the ground, Ground means the plane of the equator. How shall I say that? The xy plane, yeah, is this. And it looks horrible. And it looks like an egg. It's not supposed to be an egg, okay? It's a circle. I'm sorry if it looks like an egg. Okay, and that would be the only hint you would get. You would be asked to figure out this circle in polar coordinates, and I'm not sure if all of you would know how to do that, and this is what worried me. So before we do everything, can we express this in polar coordinates? I mean, how are you gonna set up something in r theta for the same domain inside this disk?
I could open up the x minus 1 half. Then I'll have x squared plus y squared. That will be r. And 2x, that will be on my way. That will be just.
We can find out the radius and then like double integral 1 dot dA, and we can put the limits of r and theta.
So if we were, for example, to say x is r cosine theta, can we do that? And y to be r sine theta?
Yeah.
What would we get instead of this equation, because it looks horrible? We would get this equation. Let's brush it up a little bit first. It's x squared plus y squared. And that's nice, but then it's minus twice, it's just x, plus 1 over 4, equals 1 over 4, the heck with it. My son says, don't say heck, that's a bad word. I didn't know that. But he says that he's being told in school it's a bad word, so he must know what he's talking about. So this is r squared, and x is r cosine theta. So there we are, we almost did it, in the sense that r squared equals r cosine theta is the polar equation, equation of the circle in polar coordinates, but we hate r. Let's simplify by an r, because r is positive, cannot be 0, right? It would be a point. So divide by r and get r equals cosine theta. So what is r equals cosine theta? R equals cosine theta is your worst nightmare from, I'm going to make a face. That was your worst nightmare in Calculus 2. And I was just talking to a few colleagues in Calculus telling me that the students don't know that and they have a big, hard time with that. So the equation of this circle is r equals cosine theta. So if I were to express this domain, which in Cartesian coordinates would be written, I don't know if you want to, as the double integral, we would have to do the vertical strip thingy. But if I want to do it in polar coordinates, I'm going to say, I start, well, you have to tell me what you think. We have an R that starts at the origin, and that's the R. How far does R go? R goes, for the domain inside, R goes between 0 and cosine theta.
Then why were you able to divide by r if it could have equaled 0?
We already did.
Yes, but then you just said you said you could only do that because it never equaled 0.
Right. And
Then
for
you just
0,
said-
we pull out the 1 point, or we
Okay.
take the angle that we want. We will still get the same thing. And now,
Professor, R is not the radius? What is R?
no, R will be any, okay,
Oh, I see.
yeah, so little r, what is the r of any little point inside? The r of any little point inside is between 0 and cosine theta. Cosine theta would be the r corresponding to the boundary. Say it again. So every point on the boundary will have that r equals cosine theta. The points inside the domain, and this is on the circle, on C. This is the circle, let's call it C round like that. This is C round. Okay, so the points inside have what property, that their R is between 0 and cosine theta. If I take R theta with this property, I should be able to get all the domain. But theta, you have to be a little bit careful about theta.
It goes from pi over 2 to negative pi over 2.
Actually, yeah, so you have theta will be between minus pi over 2 and pi over 2, and you have to think a little bit about how you set up the double integral. But you're not there yet. So when we'll be there at the double integral, we will have to think about it. What else did I want? All right, so did I give you the right form of f? Yes. I'd like you to compute curl f and n all by yourself, so compute. This is going to be f1, this is going to be f2, this is going to be f3, and I'd like you to realize that this is nothing but integral over CF dr. Right? So who is this animal? This is the work, guys. All right, so I should be able to set up some integral, double integral over a surface, where I have curl F times N ds. So what I want you to do is simply, maybe I'm a little bit too lazy, take the curl of F and tell me what it is. Take the unit normal vector field and tell me what it is. And then we will figure out the rest. So you say, wait a minute, Magdalena, you want me to look at the Stokes theorem over what surface? Because C is the red boundary. So you want me to look at this surface, right? The cap. So the surface could be the cap. But what did I tell you before? I told you that Stokes' theorem works for any kind of domain that is bounded by the curve C. So is this the way you're going to do it? Take the cap, put the normals, find the normals, and do all the horrible computation? Or you will simplify your life and understand that this is exactly the same as the integral evaluated over any surface bounded by C. Well, this horrible thing is going to kill us. So what's the simplest way to do this? It would be to do it over another surface. It doesn't matter what surface you have. This is the C. You can take any surface that's bounded by C. You can take this balloon, you can take this one, you can take the disk bounded by C, you can take any surface that's bounded by C. So in particular, what if you take the surface inside this red disk? The planar surface inside that red disk. Okay. Do you see it? Okay, that's going to be part of a plane. What is that plane? X plus z equals 1. So you guys have to tell me who n will be and who the curl will be. And let me show you again with my hands what you have. You have a surface that's curvilinear and round and has boundary C, the boundary C. You have another surface that's an ellipse that has C as a boundary. And this is sitting in a plane, and it's very hard to model with my hands, but this is it. You see it? You see it? Okay. When you project this on the ground, this is going to become that circle that I just erased. So this and that. We have a surface integral. Remember, you have ds here up, and you have dA here down. ds here up, dA here down. So that shouldn't be hard to do at all. Now, what is n? N for such an individual will be really nice and sassy. X plus z equals 1, right? So what is the normal to the plane X plus z? Who does? That's projection in plane. So who is this normal? For D curl F times not K but N the I don't know, another S tilde. So for this kind of surface I have another ds tilde. Okay? Alright. So who's gonna tell me who N is? Well, it should be X plus Z equals 1. What do we keep, what do we throw away? The plane is X plus Z equals 1. What's the normal? So the plane is X plus 0y plus 1Z equals 1. What's the normal to the plane?
Is it I plus k over square root 2?
I plus k, very good, but why does Xander say over square root of 2? Because it says, remember guys, that has to be a unit normal. We cannot take I plus k based on being perpendicular to the x plus z, because you need to normalize it. So he did. So he got I plus k over square root of 2. How much is curl of f? You have to do this by yourselves. I'll just give it to you. I give you 3 minutes and then I'll check your work based on the answer that we have. And in the end I'll have to do the dot product and keep going. Is it hard? Well, I should do it along with you guys. So I have ijk, ddx, ddy, dz. Who were the guys? Y squared over 2 was f1, z was f2, x was f3. Now let's see what you got. I'm checking to see if you get the same thing. Minus I is the first guy I pronounced. Let's see, the next one. Minus j,
minus
yk. And I think that's what it is, yes. So when you do the integral, what are you going to get? I'm going to erase a little bit here. You have your n, and your n is nice. What was it again, Alexander? I plus k over square root 2, right? So let's write down the integral. W will be double integral over the domain. Now in our case, the domain is this domain. This one here. Let's call it, do you want to call it D or D star or D tilde? I don't know what. Because we used to call the domain on the ground D. Let's put here D star. D star. So over D star, and the cap doesn't exist in your life anymore. You said, bye-bye, bubble. I can do the whole computation on D star. I get the same answer. So, you help me, right? I get minus 1 times 1 over root 2, am I right? A 0 for the middle term, and a minus y times 1 over root 2. Good. This is the whole thing over here. My worry is about ds star. What was ds star? ds star is the area element for the plane. This is the area element for, how can I call this, for this? For D star, not for D. It's a little bit complicated. D is a projection. So, who reminds me how we did it? D star was what times dA? This is the surface area. And if you have a surface that's nice, your surface is nice.
Areas R.
What was this equation of this surface up here? This is the ellipse that goes projected on the circle.
Cosine of the verse.
The equation of the plane. Think equation of the plane. So I erased it. So it was x. Was it x plus z equals 1? So z must be 1 minus x. So this is going to be square root of 1 plus minus 1 is the first partial. Are you guys with me? Partial with respect to x of this guy is minus 1 squared. Plus the partial of this with respect to y is missing 0 squared. And then it comes dA. And who is dA? dA is dx dy in the plane, in the floor plane. In the floor plane. This is the star is the element on this plane that projects onto the floor plane. Good. The star is going to be then square root 2 dA. Again, the old trick that I taught you guys is that this will always have to simplify with the element on the bottom of the n. Say what, Magdalena? Say it again. Square root of 2 dA. This is that magic square root of 1 plus f sub x squared plus f sub y squared. This guy, no matter what exercise you're doing, will always simplify with the bottom of n, which Xander saw it was square root of 2. Okay, so you can do this simplification from the beginning. And so in the end, what you're going to have? You're going to have double W is minus y minus 1 over the domain D in the plane, the disk in plane. The square root of 2 went away, and then you have dA, which is dx dy. Okay. At this point, suppose that you are taking the fiber. And this is why I got to this point, because I wanted to emphasize this. Whether you stop here or you do one more step, I will be happy. Let's see what I mean. So you would have minus with y r cosine theta minus 1. dA will become, instead of dx dy, you have r, very good, r dr d theta, r, so you're thinking, well, so you're thinking, I'm looking here what we have, r was from 0 to cosine theta, and theta is from minus pi over 2 to pi over 2. Please stop here. All right? So in the exam, we will not expect, on some integrals, we'll not expect that you go on and do that. We'll say set up the integral and leave it. Yes, sir.
Why did you put r cosine theta for y?
Because let me remind you, when you project the image of this ellipse on the plane, we got this fellow, which is drawn in the book as being this, okay? So we said, I want to see how I set this up in polar coordinates. The equation of the plane of the circle was r equals cosine theta, and this was calculus 2. That's why we actually don't insist too much. So if somebody would ask you guys, compute me, instead of an area over the domain, what if you compute for me the area of the domain? How would you do that? Well, double integral over 1, or whatever that is, integral, of r dr d theta. Instead of 1, you can have some other ugly integral. Looking at you, I put a star here. Theta is between minus pi over 2 and pi over 2. Because I'm moving from here to here, from here to here, okay? And r is between 0 and the margin. Who is on the margin? I start at 0, I end at cosine theta, start at 0, end at cosine theta. Cosine theta happens only for the boundary, okay? So that's what you do. Do we want you to do that? No. We want you to leave it. Yes,
He was
sir.
asking why, you had a negative y
Why
minus
should
1.
be r sine theta?
R is r sine theta, not r cosine theta.
You are so right. I forgot that x was r cosine theta, right? And y was r sine theta. You're correct. And you had a good observation. So r was in polar coordinates cosine theta, and x was r cosine theta, y was r sine theta. Very good. Okay, so do we want you, if you get something like that, we will now want you to go on. We want you to stop. Let me show you one where we want you to go on, and we will indicate it like this. Example 3. So here we just don't want you to show some work. We want you to actually get the exact answer. And I'll draw the picture, and don't be afraid of it. It's going to look a little bit ugly. You have the surface, z equals 1 minus x squared minus what? 2y squared. And you have to evaluate over double integral of the surface S. This is the surface. Let me draw the surface. We will have to understand what kind of surface that is. Okay. Double integral of curl f dot n ds evaluated, where f equals xi plus y squared j plus, this looks like z e to the xy, it's very tiny, I barely see it, e to the xy k, and s is that part of the surface let me change the marker so the video can see better. Z, this is a bad marker. Z equals what was it, guys? 1 minus x squared minus 2y squared with z positive or 0. And the hint is, I think we may give you this hint on the exam. Think of the Stokes theorem and the typical, think of the Stokes theorem and the typical tools you have learned about. Okay, what does it mean? We have like an eggshell which is coming from the paraboloid. This paraboloid is s 1 minus x squared minus 2y squared. And we call that s, but you see you have two surfaces that are bounded, that are in this picture bounded by c. The other one is the domain D. And it's a simple problem because your domain D is sitting on the xy plane. So it's a blessing that you already know what D will be. D will be those pairs xy with what property? Can you guys tell me what D will be? Well, Z should be 0, right? If you impose Z to be 0, then this has to satisfy x squared plus 2y squared less than or equal to 1. What is the C? C are the points on the boundary, which means exactly x squared plus 2y squared is equal to 1. What in the world is this curve? Who tells me? It's an ellipse. Is it an ugly ellipse? Not really. It's a nice ellipse. Okay. What do they give us? They give us x, y squared, and z times e to the xy. So this is f1, f2, and f3. So the surface itself is just the part that corresponds to z positive, not all the surface, because the whole surface will be infinitely large. It's a paraboloid that keeps going down to minus infinity. So you only take this part. It's a finite patch that I stop at. So this is a problem that's amazingly simple once you saw it one time. You don't even have to show your work much in the actual exam, and I'll show you why. So Stokes' theorem tells you what in this case? Let's review what Stokes' theorem says. Stokes' theorem says, okay, you have the work. Perform by the force F that's given to you as a vector value function along the path C, which is given to you as this wonderful ellipse. Let me put C like I did it before, C. This is not L, C. Which, what is that? Is the same as double integral over S, the round paraboloid like the church roof. S, curl F times N ds. But what does it say? This happens for any, for any, do you know the sign? Surface is bounded by C. And here is that winking emoticons from, how is that, in Facebook? Something like that. A wink would be a good hint on the final. What are you going to do when you see that wink? If it's not on the final, I will wink at you until you understand what I'm trying to say. It means that you can change the surface to any other surface that has the boundary C. What's the simplest surface you may think of? The D. So I'm going to go and say double integral over D. Curl F, God knows what that is. We still have to do some work here. I'm making a sad face because I really wanted no work whatsoever. And becomes, we've done this argument 3 times today.
Okay.
It's a K. That is your blessing. That's what you will have to indicate on the exam. That N is K when I look at the planar domain.
And ds is dA.
And ds is dA. It's much simpler than before because you don't have to project. You are already projected. You are all to the floor. You're on the ground. What else do you have to do? Not much. You just have to be patient and compute with me, something I don't like to. Last time I asked you to do it by yourself, but now I shouldn't be lazy. I have to help you. You have to help me. IJK, DDX, DDY, DDZ. Of what? X, Y squared,
Oh, that's a y squared.
and this horrible guy. What do we get? Well, it's not so obvious
ZY
anymore.
dx.
Z, prime this guy with
Oh,
respect to
ZX.
y, ZX. Very good, ZX. E to dxy times I. And I don't care about the rest. Why don't I care about the rest? Because when I prime y squared with respect to z goes away. So I'm done with the first term. I'm going very slow, as you can see, but I don't care. So I'm going to erase more. Next guy, minus.
That's
And then we'll
ZY
make an
dxy.
observation. The same thing here, I go differentiate with respect. So I have zy e to the xy. Are you guys with me or I'm talking nonsense? So look at, what am I saying? What am I saying? I'm saying that I expand with respect to the j element here. I have a minus because of that, and then I have the derivative of this animal with respect to x,
Yeah.
which is zy e to the xy j. Correct?
Yes.
Finally, last but not least, and actually that's the most important guy, and I'll tell you in a second why. What is the last guy? Zero. So one of you will hopefully realize what I'm going to ask you right now. No matter what I got here, was, what is that called? A work that is not necessary. It's a stupid work, okay? So why is that not necessary? Why could I have said star I plus star j, God knows what that is, plus 0k? Because in the end, I have to multiply in that product with k.
Oh.
So no matter what we do here, and we sweat a lot, and so no matter what we put here, it wouldn't have made a difference because I have to take this whole curl and multiply as a dot with k. And what matters is only what's left over. So my observation is this whole thing is how much? 0, thank God. So the answer is 0. And we've given this problem with the answer 0 about 4 times on 4 different finds. Okay? The thing is that many students don't study and they didn't know the trick. When you have a surface like that bounds the curve C, instead of doing Stokes over the surface, you do Stokes over the domain in plane, and you get 0. So poor kids, they went ahead and tried to compute this from scratch for the surface, and they got nowhere. And then I started the fights with the course coordinator, who didn't want to give them any credit. And I wanted to give them at least some credit for knowing the theorem, the statement, and trying to do something for the nasty surface, the roof that is a paraboloid. They've done something. So in the end, I said I want to do whatever I want, and I gave partial credit. But normally I was told not to give partial credit for this kind of attempt, because the whole key of the problem is to be smart, understand the idea, and get 0 without doing any work. And that was nice. Yes, sir?
So does that mean that all we really needed to compute of the curl was the k part? Because if k would have been something, then there would have been a dot.
Exactly.
Yeah.
But only if, guys, no matter what f we give you, if your surface has a planar boundary, say it again, if your surface, no matter what it is, it could look like geography. If your surface has a boundary in the plane xy, like it is in geography, imagine you have a hill or something, and that's the sea level, and around the hill you have that rim of the hill. Okay, that's your planar curve. Then you can reduce to the plane, and all the argument will be like that. So the thing is, you get 0 when? You get 0 when the curl has 0 here and the rest doesn't matter. Say it again. When the f is given to you so that the last component of the curl is 0, you will get 0 for the work. Otherwise, you can get something else, but not bad at all. You can get something that, let's do another example like that where you have a simplification. I'm going to go ahead and erase
So
the whole.
let's say if I knew all this step, I put work equal to 0. So
You cannot know unless you look at the f first. You see?
let's say that I put the f on top, and I put the equation, which is f dr, and I put the curl, f dot product of n. So then I said, look at it and say, oh, look, this is 0.
If you see that to be 0, you can go ahead and put 0 at the end.
Okay.
Because the dot product between k, that's what matters, the dot product between k and the last component of the curl.
Yeah.
And in the end, integral of 0 is 0. And that is the blessing, that's a blessing.
But we should also have n equal to k. If we don't have that,
Yeah, so I'm saying if, that's a problem. If, this is not going to happen, but assume that somebody gives you a hill that looks like that. And this is not a planar curve. This would be a really nasty curve in space. You cannot do that anymore. You have to apply things for the general surface. But if your boundary C is a planar boundary, having a domain in plane, then you can do that and simplify your life. Okay, so let me give you another example. This time is not going to be, okay, you will see the surprise. And you have a sphere, and you have a spherical cap. A sphere of radius r, and this is going to be, let's say r to be 5, and this is z equals 3. You have the surface, somebody gives you the surface S, that is the spherical cap of the sphere x squared plus y squared plus z squared equals 25. above the plane z equals 3. Compute double integral of f times, how did we phrase this? Did we phrase it as a, no, we said curl f and, I'm sorry, did we phrase it as work? No, curl f n over S, where S is the spherical cap. This is S. Yes. So you got this on the final. First thing is stay calm, don't freak out. This is a typical, you have to say, okay, she prepared me well. I did review on 10 problems like that. For God's sake, I'm going to do fine. Just keep in mind that no matter what we do, it's not going to involve a heavy computation like we saw in that horrible first example I gave you, second example I gave you. So the whole idea is to make your life easier rather than harder. So what's the first thing you do? You take curl f, and you want to see what that will be. ijk is going to be ddx, ddy, ddz. And you say, alrighty, then I'll have x squared yz, xy squared z, and xyz squared. And you say, well, this looks ugly, right? That's what you're going to say. So, what times I minus what times j plus what times k remains up to you to do the computation, and you say, wait a minute, the first minor is in math. No, the first minor is the name of such a determinant, it's just a silly pun. So you do xyz squared with respect to y, it's xz squared, minus prime with respect to z, dz
Well, xy squared.
xy squared. Next guy. What do we have? Who tells me? It's sort of symmetric, but not really. Y is squared. Good. It's symmetric in a way. X squared y. Right, guys? Are you with me? And for the k, you have
Y squared z.
y squared z.
X squared z. Or x squared y.
X squared z. Because if you look at this guy, so we stare at it again and we say, well, I have the derivative with respect to x is y squared z. The derivative with respect to y is x squared y squared z, and then minus x squared z. Then I have, did I write it correctly? Yes. Yes, I did, right? So this is correct. That's what matters is that I check what I'm going to do. So now I say my C is a boundary, that's a circle. So the meaning of this integral given by Stokes is actually a path integral along the C at the level z equals 3. I'm at the third floor looking at the world from up there. I have a circle at the third floor, z equals 3. And then I say, that's going to be f dot dr, God knows what, that was originally the work. And Stokes' theorem says, no matter what surface S you're going to take to have a regular surface without punctures in it, without holes, that is bounded by the circle C, you're going to be in business. So I say, the heck with the S, right? I want a D, and I want that D to be colorful because life is gray enough. Let's make it D. That D has what meaning? Z equals 3. I'm at the level 3, but also x squared plus y squared must be less than or equal to something. Could anybody tell me what that is? How?
16.
So how do I know? I will just plug in 3 here. 3 squared is 9. 25 minus 9. So I get x squared plus y squared equals 16. So from here to here, how much do I have? 4, right? So that the radius of that yellow domain, no yellow orange domain will be 4. Okay, so let's write down that thing. Let's call this D. This domain is going to be called D. And then I have this curl F. And who is N? N is K. Why? Because I'm in a plane that's upstairs. And I have dA. Because whether the plane is upstairs or downstairs on the first floor, dA will still be dx dy. And, okay, so now let's compute what we have backwards. So this times K will give me double integral over D of y squared times, who is Z? I'm in a domain D where Z is fixed.
3.
Z is 3. Minus x squared times 3. And
dx dy.
I just came up with this problem. If I were to write it for the final, I would write it even simpler. But let's see, 3 and 3, and then nothing, and then dA, dx dy, right? Over the D, which is x squared plus y squared, is less than or equal to 60. How do I solve such an integral? I'm going to make it nicer. Okay. So how would I solve such an integral? Is it a headache, a painful thing? Huh? Polar coordinates, and somebody's going to help me. And as soon as we are done, we are done. 3 gets out. And instead of x squared plus y squared less than 16, I have r between 0 and 4, theta between 0 and 2 pi. I have to take advantage of everything I've learned all the semester. Knowledge is power. What's missing? R. A 3 got out, and here I have to be just smart and pay attention to what you told me, because you told me, Magdalena, why is r sine theta, not r cosine theta? And I'm grateful. This is r squared, sine squared theta, minus r squared, cosine squared theta. So what have I taught you about integrants that can be expressed as products of a function of theta and a function of r? That they are a blessing from God. So you have 3 integral from 0 to 2 pi minus 1. I have my plan when it comes to this guy because it goes on my nerves. Alrighty, do you see this? D theta. Do you know what I'm coming up with? Cosine of the double angle. Very good. I'm proud of you guys. If I were to test, there was a test by Project Next for the whole nation. Only about 10% of the students remember that by the end of the calculus sequence. But I think that's not, that doesn't show weakness of the calculus programs. It shows weakness in the trigonometry classes that were either missing from high school or whatever. So you know that you are in power. Now times what? Integral from 0 to 4
Of r squared, r cubed.
r cubed, which again is wonderful that we have. And we should be able to compute the whole thing easily. Now, if I'm smart,
It's 0.
how come it's 0?
Because it is called cosine to theta integral is sine to theta. And
Right.
over 2 pi.
So the sine to theta, whether I put it here or here, it's still gonna be 0. The whole thing will be 0. So I played the game. Maybe I should have given such a problem when we wrote this edition of the book. I think it's nicer than the computational one you saw before. But I taught you this trick so you remember it for the final. And you have to promise that you remember it. And that was the whole essence of understanding that the Stokes theorem can become Green's theorem very easily when you work with a surface that's a domain in plane, a planar domain. Don't go ahead and use. Are you done with this? Okay. So you say, okay, so what else? This was something that's sort of fun, I understand it. Is there anything left in this whole chapter? Fortunately or unfortunately, there is only one section left, and I'm going to go over it today. And
Can I ask you a quick question about
yes, sir.
36 before you move on?
Move on.
I was an idiot, and when I was
No, you
writing
were
these
not.
down, I
Wait.
missed a variable. So I have the integral of f dr over c equals double integral over f curl f dot n ds. I didn't write down what c was. I didn't write down what this c was.
The C was the whatever boundary
Okay.
you had of the surface S, and that was in the beginning when we defined this thing, when we gave the general statement for the theorem. So I'm going to try and draw a potato. We don't do a very good job in the book drawing a solid body, but I'll try and draw a very nice solid body, and let's see. You have a solid body. Imagine it as a potato, topologically a sphere. It's a balloon that you blow. It's a closed surface. It closes in itself. And we call that R in the book. R is a solid region enclosed by the closed surfaces. Sometimes we call such a surface compact for some topological reasons. Let's put S. S is the boundary of R. We assume our old friend F to be a vector value function. And again, if you like a force field, think of it as a force field. I'm not going to tell you what it is. It's some C1 function, is differentiable, and the partial derivatives are continuous. The magic thing is that this surface must be orientable, and if we are going to immerse it, it's a regular surface, then of course n exists. And the orientation, guys, doesn't have to be outwards. It could be inwards in general, but let's make the convention that n will be outwards by convention. So we have to have an agreement like they do in politics between Fidel Castro and Obama. But by convention, whether we like it or not, let's assume the normal will be pointing out. Then something magic happens. And that magic thing, I'm not going to tell you what it is, but you should tell me if you remember what the double integral was in this case in terms of physics. Shut up, Magdalena, don't tell them everything. Let people remember what this was. So what is the second term? This is the so-called famous divergence theorem. So this is the divergence. If you don't remember that, we will review it. dv is the volume integral. I have a triple integral over the solid potato, of course. What is this animal for? Okay, take some milk and strain it and make cheese. And you have that kind of piece of cloth and you hang it. And the water goes through that piece of cloth. And it had this kind of suggestive image should make you think of something we talked about before. Whether that was fluid dynamics or electromagnetism, electric circuits, this has the same name. F is some sort of, some sort of field, vector valued field. N is the outer normal in this case. What is the meaning of that? For $1, which I don't have, it's a 4-letter word, it's an F word. Very good, I'm proud of you. Who said it first? Aaron said it first. I owe you $1. You can stop by my office, I'll give you that. So the flux, he did.
Yeah, silently.
Aaron is a mind reader. So, okay, so the flux in the left-hand side, this thing you don't know what it is, but it's some sort of potato. What is the divergence of something? So if somebody gives you the vector field F1 like F3K, where these are functions of xy, z, you are in R3. What is divergence of F? By definition, remember section 13.1? Keep it in mind for the final. So what do we do? Differentiate the first component with respect to x, plus differentiate the second component with respect to y, plus differentiate the third component with respect to z, sum them up, and that's your divergence. Okay? How do engineers write divergence? Not like a mathematician or like a geometer. I'm doing differential geometry. How do they write it?
Triangle dot.
Nabla dot F. This is how engineers write divergence. And when they write curl, how do they write it? They write nabla cross product because it has a meaning. If you think about operator, you have ddx applied to F1, ddy applied to F2, ddz applied to F3. So it's like having the dot product between ddx, ddy, ddz operators, which would be the nabla operator, acting on F1, F2, F3. So you go first, plus, second, plus, third, right? It's exactly the same idea that you inherited from the dot product. Now let's see the last two problems of this semester, except for the review, but the review is another story. So I'm gonna pick one of your favorite problems, and okay, example 1. Remember your favorite tetrahedron. I'm gonna erase it. Instead of the potato, you can have something like a pyramid. And you had example 1. Let's say we have that. Somebody gives you the F. I'm going to make it nice and sassy because the final is coming and I want simple examples. And don't expect anything ugly. Really nice examples also on the final. Apply divergence theorem. In order to compute double integral of f dot n ds over s, where s is the surface of the tetrahedron. In the picture. And that's your favorite tetrahedron. We've done that like a million times. Somebody gave you a, shall I put 1 or 8? 1 because Nitish is in easy mode right now. So you have the plane x plus y plus z equals 1. You intersect with the axis of coordinates, you take the planes of coordinates and you form a tetrahedron. That tetrahedron is a little bit beautiful that it has 90-degree angles at the vertex and it has a name, OABC. OABC is the tetrahedron and the surface of the tetrahedron is S. How are you going to do this problem? You're going to say, oh my God, I don't know. It's not
Well,
hard.
it looks like you're gonna use the formula you just gave us.
The
and-
divergence theorem,
And the
considering-
divergence for that's really easy, it's just a constant.
right, and we have to give a name to the tetrahedron. Let's be the solid tetrahedron. And its area, its surface is S. Instead of the potato, you have the solid tetrahedron. So what do you write? Exactly what Sandra told you. Triple integral over T of what? The divergence of F, because that's the divergence theorem, dV. Well, it should be easy because divergence of, just as you said, divergence of F will be a constant. How come? Differentiate this with respect to X, 2. This with respect to Y, 3. This with respect to Z, 5. Last time I checked, this was 10 when I was little. So 10. So 10 says I'm going for a walk. And then triple integral of the volume of 1 dV over T. What is this? Well, because I taught you how to cheat. Yes, but what if I were to ask you to express this in terms of as a
Domain.
yeah, integrate one at a time. So you have 1 dz, dy, dx. I'm doing review with you. From 0 to 1 minus x minus y. From 0 to 1 in the world. 1 minus x. From 0 to 1. And how did I teach you how to cheat? I taught you that in this case you shouldn't bother compute that. Remember that you were in school and we learned the volume of the tetrahedron was the area of the base times the height divided by 3, which was 1/2 times 1 divided by 3. So you guys are right. The answer is 10 times 1 over 6. Do I leave it like that? No, because it's not nice. So the answer is 5/3. Expect something like that on the final. Something very similar. So you'll have to apply the divergence theorem and do a good job. And of course, you have to be careful, but it shouldn't be hard. It's something that should be easy to do. Now, the last problem of the semester that I want to do as an application of divergence theorem is over a cube. So, I'm going to erase it, the whole thing, and I'm going to draw a cube, which is an open top box upside down. Say it again, an open top box upside down, which means somebody gives you a cubic box and tells you to turn it upside down. And you have from here to here 1. All the dimensions of the cube are 1. The top is missing, so you have this face is missing. The bottom face is missing. Bottom face is missing. Let's call it, what in the world shall we call it? F1, because it was the top, but now it's the bottom. Okay, and the rest are F2, F3, F4, F5, and F6, which is the top. All right, and I'm going to erase. And the last thing I will ask you for this section is to do the following. What do I want? Evaluate the flux double integral over SF dot NDS. You have to evaluate that. For the case when F, I usually don't take the exact data from the book, but in this case I want to because I know you'll read it and I don't want you to have any difficulty with this problem. I hate the data myself, I didn't like it very much. The unit cube, it's a unit cube, okay? So x must be between 0 and 1, y must be between 0 and 1, including them. But z, attention guys, z must be between 0 open, 0 without 0, because you remove the face on the ground, z greater than 0 and less than and or equal to 1. And do I want anything else? No, that is all. So let's compute the whole thing. Now assume the box would be complete. If the box were complete, then I would have the following. Double integral over all the faces, F2 union with F3 union with F4 union with F5 union with, oh my god, F6 of F dot n ds plus double integral over what's missing, guys? F1 of n f dot n ds, f like the linear, that's the flux, f dot n ds. If it were complete, that would mean I have the double integral over all the 6 faces. In that case, this sum would be, I can apply finally the divergence theorem, and that would be triple integral of, oh God knows what that is, divergence of f dv over the cube. What do you want us to call the cube?
C.
C is usually what we denote for the curve.
How about Q?
Beautiful. Sounds good. I like that. Q. Q is the cube inside the whole thing. Unfortunately, this is not very nicely picked. Just to make your life miserable. So you have d dx of xy. There is no j, at least that. d dz minus z squared. As soon as you're done with this, since I gave you no break, I'm going to let you go. So what do we have? Y minus 2z. Does it look good? No. Does it look bad? No, not really bad either. If I were to solve the problem, I would have to say triple, 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 y minus 2z. And now, oh my God, dz, dy, dx. I sort of hate a little bit of computation, 0 to 1, 0 to 1, 0 to 1, but this is Fubini's theorem. So is there anybody missing from the picture so I can reduce it to a double integral? X is missing, so I say if there is no x inside, I go, what is integral from 0 to 1 of 1 dx? 1. So I will rewrite it as integral from 0 to 1, integral from 0 to 1, y minus 2z dz dy. Is this hard? No, but it's a little bit obnoxious. When I integrate with respect to z, what do I get? yz minus z squared, well, not bad, between z equals 0, 1 down, z equals 1 up, z equals 0 down, dy. So it's integral from 0 to 1 of what? When z is 0 down, I have nothing.
Yeah, 1 minus, y minus 1.
Y minus 1, not so bad. Not so bad, dy. So I get y squared over 2 minus y. between 0 and 1. What do I get?
Negative 1/2.
Negative 1/2. All right, let's see what we got here. Yeah, they got negative 1/2. And now I'm asking you, what's going to happen? Our contour is the open top box upside down. This is what we need. This is what we
Then you just
Neat.
subtract the double integral.
We just have to compute this fellow. We need to compute that fellow. So how do we do that? How do we do that?
What is the problem asking for again?
So the problem is asking over this flux, but only over the box's walls and the top. The top, 1, 2, 3, 4, without the bottom, which is missing. In order to apply divergence theorem, I have to put the bottom back and have a closed surface that is enclosing the whole cube. So this is what I want. This is what I know. How much is it, guys? -1/2. And this is again what I need. Right? That's the last thing I'm going to do today.
It's just
Who's
F
gonna
times
help
K
me?
dA.
Huh?
F times K dA.
Let's compute it. K is a blessing, as you said, Xander. It's actually minus K. Why is it minus K? Because it's upside down and it's an outer normal. It has
Oh, it
to
needs to get out of the normal.
get
Okay.
out.
Yeah,
So
that's right.
minus
That's
K.
right.
But it doesn't, I don't know. Well, the sign matters, so I have to be careful. F is, Z is 0, thank God. So that goes away. So I have X, Y, I, dot product with minus K. What's the beauty of this? It's 0. Yay, 0. So the answer to this problem is -1/2. So the answer is -1. And we are done with the last section of the book, which is 13.7. It was a long way. We came a long way. What I'm going to do next time, and the times to come. I'll first of all ask you from now on, you want a break or not, because I didn't give you a break today. We are not in a hurry. I will pick up exams and I will go over them together with you. And we'll solve. By the time we finish this review, we would have solved 2 or 3 finals completely. We will be doctors in Calculus 3. And so the final is on May 11th at 10:30 in the morning. I think.
It's the 11th, the 12th is
The 12th is the other class. We're splitting into 2
I have it
classes.
written down on my calendar.
It's May 11th, 10:30 in the morning. On May 12th, there are other math courses that have a common final. Unfortunately for them, they start at 4:30. I'm really blessed that I don't have that case. They start at 4:30 and they end at 7 o'clock. And imagine how risky you feel when you take that final in the night.
So much. I was on like number 6.
Good luck with the homework. Ask me questions about the homework.
I didn't know
Have them.
all the people wanted.
Jason, I'm gonna be here on Thursday.